So let's try to see if this works. Okay, that's good. Yes. So I want to start by thanking the organizers. I'm very happy to be here in Fes. It's also my first time in Morocco. It's a truly beautiful and special country. I thought I would bring something a bit original today. But it's actually linked a bit to some of the talks we heard this morning. So let's start with the following idea. So here on these slides, I have two pictures of 500 points that are randomly generated. And let's say I want to describe these 500 points somehow. What are some central tendency? Well, for the point on the left, what I can do is typically I can calculate the mean. It says that, okay, a good central value for this point is around 3 and 1.85. And then I have a covariance matrix, which I can compute, which gives me 1 here, 4 here. And it says that roughly there's a lot more variance here and maybe it doesn't look like it because of the scaling, but there's a lot more variance here in the y direction compared to in the x direction. And let's say we want to do the same for the things on the right. Well, how do we do that? So these are on a manifold. We can't really add up points on a manifold. If you add 2 points on the manifold, on a sphere, for example, they're no longer on the sphere. And if you just take the linear average, it's no longer on the sphere. And how does then covariance work in the setting? That's what we were talking about. So to put it another way, is there a way we can define an average between Fes and Shanghai without ending up inside the Earth, but actually at some point on the Earth? And this is not just theoretical fun things. This is something that has real-world applications. For example, for diffusion MRI, positive symmetric matrices are a very important space. This is not a vector space. So you cannot not necessarily add them and make means. There's also some Hermitian matrices here. Let's see if this one works. Hold on. No, I don't have the, but I do have the. Sorry, I think we'll just skip this and stick with the others. Sorry about that. Similarly, if you want to work with radar signal processing, you can work at Hermitian positive definite matrices. So tuplets here just means the diagonal is just one constant value all the time. Or you can have the space of faces represented by level curves. You can parameterize these level curves in a certain way, pick some landmarks where they go through, and make the space out of it, right? And here it's then useful to have a sort of mean. So if we have a nonlinear space, so we can't add points, what can we then do? Well, one way is that, okay, if we have a Riemannian manifold, then at least we have like a distance, right? So we have the shortest, in all Riemannian manifolds, we have a distance as the shortest path between all 2 points. And we can use this one, that's an intrinsic quantity, that we can use to consider, for example, a mean. So here, of course, G is a Riemannian metric that I think you're well aware of. One thing to consider a bit is the importance of geodesics also when it comes to Riemannian metrics. So in some cases, like the hyperbolic space that we saw this morning, or the sphere, we have explicit formula for the distance. But a lot of Riemannian manifolds, we don't have, it doesn't need to be very complicated before we don't have any distance at all, right? But when it comes to computation, the geodesics equations, they're always rather easy, right? So it means that, okay, if I really need a distance between 2 points, I can solve the geodesic equation with some initial condition, shoot off, see where I land, and then iterate with like gradient descent or something similar until I hit my final point and find the distance that way. So the fact of having sort of a geodesic equation is actually very, very useful in practical terms to find the distance from the manifold is different. One thing I wanted to emphasize here in the setting is, okay, a Riemannian metric, it doesn't necessarily, so in the beginning I showed you the sphere, which is a subset of Rn. But of course, in general, as we saw this morning, we can have things like the Poincare hyperbolic plane, where it's a disk, but where the distances sort of increase as you go to the boundary, and hence it makes sense to do traveling within the center in order to avoid becoming very long. We also have this thing called Gabriel's score, where you can consider this as a functional plane where the distances becomes very large as you go to the center. And again, this is not just theoretical. For example, in the previous thing I mentioned with the positive definite symmetric matrices, you really don't want to do some sort of numerical error which will push one of the eigenvalues to 0, right? And then it might make sense to have a Riemannian metric that acts like this when you approach a C group 0 eigenvalue. So then when you're doing your numerical applications, it's infinitely long to reach the 0 eigenvalue, and that makes sure that you stay far away from this point. Okay, having the distance, we can actually define a mean using this distance. So what we do is, I'm saying that, okay, if I have a collection of points, what I'll compute is I take some x, I'll compute the distance as square, 1 over n, and then what I do is I say that the mean is the value of x that minimizes this function. So R mean means that I'm not taking the minimum, I'm taking the x that gives me the minimum. So in other words, I'm saying that the mean is the x that minimizes this function. So it's the point that minimizes all of the distances squared combined. And this is the same as the usual mean in Rn when you are working here. I didn't change the definition for flat spaces. What's a bit strange, of course, is that if I'm in a curved space, having a mean like this is not necessarily unique. So you can imagine a sphere, and you place all your points rather evenly around the equator. Well, there's no way of saying whether the North Pole or the South Pole is the best mean for that kind of set, right? So in general, in curved spaces, more precisely in spaces where you allow positive curvature, you can have non-unique means. This doesn't occur for non-negative curvature, but it does occur for positive curvature. And then what do you do if you want higher moments? What if you want covariance or test some other higher moments? Well, one thing you can do is you can use the Riemannian logarithm, right? So for every point, there is a unique unit vector. That's the initial condition for the geodesic. You can take the logarithm that sends the point to that initial condition. Then you can start off, you just found your mean on the previous slide. So then you can start off by sort of applying this log, Now the log isn't necessarily defined everywhere in your manifold, but it's defined in some neighborhood close to your mean, so you can linearize your set of points around the mean, and then you can compute as if you were in Rn after that. So this is very concrete, and it's how things usually are done when it comes to means in nonlinear spaces. One thing to notice is that through this linearization process, we're keeping all the distances from the mean, but we're ruining all the other distances in between, right? So what I will pose to you today is a bit of an alternative approach. So the rest of the talk is centered around the diffusion mean. And the idea of the diffusion mean, this uses the fact that we actually know what the Brownian motion is on a Riemannian manifold. Now, what is a Brownian motion? Well, it's named after Robert Brown, who discovered it while looking at small pollen in water. So these pollens are getting bullied all the time by the water molecules that are hitting it, and so they form a rather irregular pattern. And if you compute it, the curves that it follows are quite bad, but if you look at the probability of where it is at any given time, well, it's actually rather nice. So the final properties of the Brownian motion is as follows. So I'm doing the standardized one, so this one will start at 0. It will be a curve with continuous paths. It's so that if you have two disjoint increments, if you know what it does on one part of, if you know the part of the curve at an earlier time, if you look at a later time, they will be completely independent. And finally, increments are actually follow a rather nice distribution. So they're normally distributed starting at 0 with variance that scales with t minus x, depending on the timing. So in particular, if you look at this Brownian motion here, and you look at where it is at time t, that is given by a multivariate normal distribution with variance t. You can also write it this way, that the probability of b of t being in any given set is given by this integral. And the important thing is that the way we're going to think about this is we're going to think about this as some sort of random curve where the probabilities of where it is at a given time is given by the normal distribution. Now, what's nice about curves is that curves in flat spaces and curves in non-flat spaces are not very different. So Rn and the sphere are very different, but the curve starting at 0 in Rn and the curve starting at the North Pole at the sphere are actually in one-to-one correspondence. So how did that work? Well, let's say you have a curve on, for example, the sphere. You can take the derivative. The derivative is a vector field along the curve. You can parallel transport that to the identity, and that gives you a curve at one fixed vector space, right? Or, sorry, I said the identity, the starting point of the curve. So you take a curve, take the derivative, parallel transport it back to where the curve started. You now have the derivative represented as a curve in a vector space. And then you can see, okay, that's the derivative of some other curves. You can integrate that. That's the correspondence. And this goes both ways. I can start off with a curve in my tangent space and then parallel transport it and continuously solve this equation. So the connection is given by, here omega is a curve in a flat space, tangent space at the initial point. And this bars here denotes parallel transport along the curve, and gamma t is my curve in my manifold. And the way you can picture this is that you draw omega on the table, and then you roll the ball here, in this case, along the curve without twisting or circling. And that's essentially what you're doing here. And that gives you one-to-one correspondence between curves in the flat space, starting at 0, and the curves on your manifold starting at a given point. And you can do this for any manifold, and it's a one-to-one correspondence as long as your curves cannot fall off. They need to be complete.
If the curve is regular, yeah? If the curve is regular.
Yeah, okay, let's say it's smooth curve for now. And let's ruin this immediately in the next slide. So the point is we can actually do this with a bad curve as well, because we have stochastic calculus that is which has this idea that you can actually integrate curves that are much worse as long as you know something about their probability distribution. So what you can actually, even though here this works as long as I have a derivative, this integral we can actually make sense and have a way of rolling our manifold along the Brownian motion, even though it's not differentiable almost everywhere, because we're using sort of the probability and the abilities of stochastic integrals. If you want to go really into detail, what you're actually doing is that you're solving Stratonovich SDE on the frame bundle. The frame bundle was mentioned earlier today. It has a canonical basis of vector fields corresponding to the Levi-Civita connection, and Stratonovich SDEs with respect to vector fields makes sense, and so you're solving it. If you're not familiar with that, just know that when you have random curves, even though they're very bad, you can actually integrate with them, and we can actually take advantage of this when doing it on a non-linear space. So that means that because of this, we do know what a Brownian motion is on any non-flat space. If you want the details, you can think of it as follows. What happens if you roll this Brownian motion on the table right here onto your manifold is that the probability distribution for this where this process is at any given point, that's given by some density, and this density is actually the heat kernel of 1/2 of the Laplacian. So if you want to solve, if you solve the heat equation with 1/2 of the Laplacian with initial point x0, that actually gives you the probability of where this is at any given time. And then from this, what we can do is we can find a mean in terms of this probability here. So the idea is to say these are the distributions here, they are sort of the normal distributions in our non-linear space. So what we can do is we can say that our t-diffusion mean is the initial point we need to choose in order to maximize the probability of the diffusion process ending up at our point set. Now, of course, our point set is 0-dimensional, so the probability is 0, but you can make this formal by having some small epsilon balls, maximizing the probability, and let those epsilon balls stretch to 0. So here's the actual formula. In place of the distance in square, we now have that we want to minimize, so we want to maximize the probability, and that's the same as minimizing minus the log probability. So the diffusion mean is then the x value which minimizes this function. And if we take the limit as t goes to 0, we have the short asymptotics of the heat kernel, which let us approach the usual Frechet mean, like that I talked to in the beginning, the one that minimizes the distance as well. So why did someone want to introduce this diffusion mean? It seems a bit like complicated. Sorry. But well, the idea is that, particularly on positively curved manifold, what you usually will want from a mean is that you have some sort of like law of large numbers. So like if you have some probability distribution with a certain mean and you take samples of them, you want that as you calculate the mean of those samples, let those samples go to infinity, then you approach the true mean of the random variable. And it turns out that with the Frechet mean, you have a probability of, problem with what's called smeariness, which essentially means that it's converging to this true mean a bit slow. Like, so it means that if you have even high number of samples, you can't be really sure that their mean represent something that's close to the true mean. And so the idea was to introduce the diffusion mean a bit to solve this problem. It shows that it has some positive qualities when it comes to the smeariness, but it's still an open question whether the diffusion mean is smeary or not, whether it converges fast enough to the true mean. But what we are going to do today is to solve the sort of other problem that I mentioned in the introduction, where I talked about if you want higher moments with the Frechet mean, you have to sort of flatten out your space. So is there a way we can introduce a covariance here on our non-flat space? So have a way to talk about normal distributions on non-flat spaces and use that to define a covariance. That will be sort of the main topic of my talk, diffusion mean and covariances. So this is based on a joint work with Stefan Sommer from Copenhagen. So what I will mainly focus on today is this first paper here. And if I have time, which I doubt I will have, there's some extra stuff about this after the slides. But we'll mainly focus on this most probable path idea and diffusion mean with covariance. So what we're going to do is that we are again going to consider this idea that we have a correspondence between curves on flat space and non-flat space. So if I want a normal distribution where I don't have a really trivial covariance, where I have some sort of covariance matrix, well, what I can do is I can take the Brownian motion, which was, I remember, had T times the identity matrix as its covariant matrix at time T, and I can multiply it with the square root of some positive definite symmetric matrix, suddenly have something that's normally distributed according to that covariance. And then I can do the same. I can now take this stochastic process here, so and this gives me an output of random curves. I can roll along those random curves, just as before, and I can now say that, okay, if I solve this stochastic differential equation, start at some point x0, and roll along this, where I put this as some covariance matrix, so this will actually be a symmetric transform of at the tangent point x0, then I say that the normal distribution at x0 and at t, sigma is the density of that process. So now I've defined normal distributions on a nonlinear space. One important thing that happens here is that I'm breaking something called the Markov property. Now, what is the Markov property? Well, the Markov property says that, okay, so if I have something that's moving and wherever it is, it follows the normal distribution, right? Then if I know where it is at time s, then, so if I know where it is at time 1, for example, and I'm wondering where it is at time 2, then I can say that it's normally distributed in variance 1, centered at where it was at time 1. But it doesn't really matter how it got to wherever point it is at time 1, right? That really doesn't matter. The Markov property is that the history of the curve up to point S does not affect the probability, only the final point. And introducing something like this actually breaks this property because of holonomy. So another way of viewing what it means to be flat or non-flat is if you do parallel transport along a curve, does it give you the identity every time, or does it give you something else, right? If you start at some point, go around the curve and come back, did you rotate your vector field, or did it stay still? For the original Brownian motion, we also have this problem that if we take it, you rotate it around the loop, and it comes back, it may be rotated. The only but the point about the Brownian motion is that it's rotationally invariant. So if I take a Brownian motion, then it has equal probability of going in any direction, and rotating it does not change it. But now that I introduce some symmetric matrix here, now there will be some directions where it's more likely to go, where this matrix has higher eigenvalues, and these will not be the same. And so now it actually matters how my random process gets to a point, because parallel transport depends on path, right? And so if I move a symmetric matrix along a path, it may be turned in one direction along one path, and in a different direction along a different path. So the way we solve this problem is that you can see that this process downstairs, solving this equation, is actually a projection of some Markov process which lives in a larger space. So this larger space I wrote as sim plus tm, and you can basically consider that I have my manifold, and then at every point I glue all the symmetric transformation from each tangent space to itself. So I can take my manifold, I can take the endomorphism bundle, and I take the subset of those that are symmetric and that have positive eigenvalues. So that gives me a fiber bundle over every point, and just working with these covariance matrices at every point, I can now get something that's a Markov basis. Now with this initial condition here, and then I have one initial condition on the point, what I can do is I can now have this density which says, okay, this is the infinitesimal probability of some random process starting at x of t and with covariance matrix sigma ending up at y. So basically the probability of this x of t being anywhere will be the integral over this density. And then as before, I can define the mean and the covariance as the best x and the best sigma to choose in order to make this as small as possible for a given point. And here something interesting happens. So before, when I went at time equal to 0, the result was that I got the distance squared. In this case, I don't get the distance squared. What I do is I do get a distance square, but it's not on the manifold. So what I get is a distance here, which is on the symmetric, this bundle, fiber bundle of symmetric tensors. And it's the distance between my initial symmetric tensor and the fiber over the final point. And the distance will follow something called a sub-Riemannian distance. So it's not will not be a Riemannian metric, it will be a sub-Riemannian metric. Now what is a sub-Riemannian metric? A sub-Riemannian manifold is defined as follows. So you have, it's similar to a Riemannian manifold, but with some severe restrictions on where you're allowed to go. So I start off with a connected manifold, and I have a sort of metric tensor, but it's not defined for all vectors. It's only defined on a sub-bundle of permitted directions. So I can't, so I only have a given length of some of the vectors, not all of them. Another way to think about it is, perhaps a better way to think about it, is that there are only some directions that have finite length, and the other directions have length infinity. And so you're completely blocked from going in that direction, because it will make your curve way too long. If you have a curve just going in these permitted directions of the subbundle, it's typically called horizontal. And just like in Riemannian geometry, we can now define lengths as the infimum of two curves connecting each point, but now with the only restriction that we're not considering all curves, we're considering the only curves of finite length, which is the curve in this permittable E1. So just to give you some pictures, this is the simplest sub-Riemannian manifold. So this is sort of the sub-Riemannian equivalent to the Rn. The very easiest sub-Riemannian manifold we can think of. So take R3, and the permitted directions are given, so I have directions dx, dy, and dz, but I'm not allowed to move in just up or down. But I can, if I move in the x direction, I am allowed to also move a bit in the z direction according to the choice of coordinate of y. And similarly, if I move a bit in the y direction, I'm also allowed to move a bit up and down in the z direction. So the way this works is that if you draw a curve, if you take the oriented area of that curve, that tells you how much you will go up and down. So a commonly used phrase is that in this geometry you can't take the lift, you can't go up and down, but you can take the stairs. So you can do a workaround and use your curve motion in the x to y direction to go up and down. So here is a picture of a subbundle. This is what this subbundle looks like in this geometry. Here I've drawn all the planes in the different direction in the xy plane. So this is the way to think about it, is that every point you have a subspace of permitted directions. And this is what the ball will look like in this geometry, where instead of looking like sort of a ball, it looks more like an apple where there are two singularities at the north and south. So what is the sub-Riemannian metric in our case, where we have, when we're trying to do this covariance? Well, our n, so the manifold that we are looking at distances at, well, that's all of these, is the manifold along with the symmetric transformation of all the tangent spaces pasted at every point. So you can imagine that taking sort of the space of all possible covariances and made that into a certain space of its own. What is the permitted direction? Well, the permitted direction are only parallel transport here in this geometry. So I'm allowed to change from one covariance to another as long as I do it by parallel transporting. So I cannot just make one of the eigenvalues longer or rotate it in place somehow. I have to do it by parallel transporting it along a certain curve. And my distance is that I'm saying that these parallel transport curves, they have shorter length if they move along in the direction where the covariance matrix have a large eigenvalue compared to a direction where it has a small eigenvalue. So where if it's spreading much in one direction, then this is cheaper for the curve to travel than the other. If we do it with math, it works as follows. If you want to parallel transport a covariance matrix, what you do is you go with a curve, and then the parallel transport means taking it back to the starting point, use your symmetric transformation, move it back. Now you have a symmetric transformation of the tangent space at the final point. And the way we define lengths of curves is that okay, so these curves are only defined using parallel transport. So we define, so the length of these curves are the same as the length of the underlying curves in G, only difference being that we apply this covariance matrix inverse, which again makes it cheaper to go along directions with large eigenvalues, because it means I'm dividing by a large number, right? If you're thinking of this in an eigen direction, this makes this easier. In an eigen direction, this is just multiplying with a constant. And then if the sigma multiplies with a large constant, the sigma inverse will divide by a large constant, and it will be cheaper, and your curves will have shorter length compared to this. And this is the final idea, is that we're going to use sort of this sub-Riemannian distance here to approximate this diffusion. Because the actual density here is actually pretty difficult to compute. Then you have to really do a lot of Monte Carlo simulations, right? So we're going to try to approximate it here. So we have one term depending on the distance, and then we have this log determinant of sigma, and that's the reason for that is that if we just consider this distance, then just having as I said before, it's cheaper to travel along directions where the sigma have large eigenvalues. So if I don't have any restrictions on sigma, then I can just make it as I can make the covariance matrix as big as possible, have the largest eigenvalues as possible, and that will be the shortest, right? So I have to compensate it a bit, that I'm not considering area, and so this becomes this approximation here. But with a few quick computations, we can essentially get it down to a scaling term, which is uniquely determined by this minimization problem, which considers all covariance matrices with determinant 1. So finding this mean comes down to just restricting to covariances with determinant 1, and then you just scale them out. And then, as I said in the beginning, when I talked about geodesics and ODE and the geodesic equation, what we want is we want some way to actually compute this distance, right? If I want to have find the minimum of this thing here, I need to be able to compute it somehow. So I need to somehow put it into my computer, and my computer needs to minimize it. And the easiest way is to then find some sort of geodesic equation, and the analog of this thing here is something called the most probable path. So this has already a known term in probability, and it basically means the most, if I draw a path between two different points, and then let some Brownian motion go, or some other stochastic process go, and then I want to have the largest possibility of this process staying random curve, staying close to my curve. Well, what is the curve I then should follow if I should maximize the probability? And so in this setting, what we then want is some curve, which is defined by parallel transport, going from some initial condition to some final point y, or the fiber of some final point y, and matches this exactly. So how do we find these sort of curves? And notice that, okay, if I put the initial condition equal to the identity matrix, then this is just the identity, and I'm back to minimizing geodesics. Right? So if I put if my covariance is the identity, then it's just the geodesics. So these generalized sort of geodesics for a nonlinear space. And then the big main result from our paper is that if you want to find these most probable paths, then they satisfy the following equation. So it's given by the covariant derivative of the curve, which follows a curvature term, and this curvature term itself is determined by the following equation. So it's a bit more complicated, but it means that there's basically a two-vector that is parallel, whose derivative in a parallel frame looks like a curve multiplied with the covariance. And then we have this final condition, which is that at the final point this two-vector should be 0. So two-vector is a vector field wedged a vector field along the curve. So and why do we have this 0 here? Well, it's because we're trying to sort of hit the fiber here, right? And so it's sort of, you can consider as sort of if you're trying to hit like a plane, like you want at the final point to hit orthogonally, right? So it's sort of the same thing here. We're trying to hit a fiber, and then the final optimality condition then becomes that this chi, should sort of hit orthogonal at the final point. That's this final condition here. And so you can, once we have this curve, we can now use a solving algorithm that sort of solves this, where we're trying to then minimize this chi of, take a different initial condition, and then when you minimize the chi of t, because you know that it will be 0, and the distance of the final point to y with respect to some initial condition. And notice, I'll tell you one thing to notice about this condition is first, if the curvature is 0, then this just becomes a normal geodesic equation. So these types of curves you don't see in flat space at all. Also, if you put this equal to the identity matrix, then you just get gamma wedge gamma, which is 0, and the final condition is 0. So the chi has to be 0. And so you also just get geodesics. If you move along an eigenvalue of this sigma, then you get multiplied by the constant. Again, this is 0. Again, you just get a geodesic. So it's really, these types of curves are really a combination of doing the statistics in nonlinear space. And I'll show you what it looks like in one example. So here we have the two-sphere. And on the two-sphere, we can actually solve this equation explicitly. So the way they work is that if I move, I start off with, here I start off with in North Pole, and I have a covariance matrix which is 2 in that direction. So it's cheaper for me to go, let's say, this way, and on the side, one view from the top, towards this cheapest direction in order to reach their place. And the equations they're following, or more precisely the angle, is that the angle is following the pendulum equation. And this chi is that so the angle is actually dropping by a pendulum, and this chi equal to 0 means that they are exactly hitting when the pendulum is about to turn. So it's a certain angle here in the middle, and they are doing a pendulum motion around it. So it's a very nice geometric thing that comes from asking questions, not what is the shortest path, what is the thing, but questions from statistics. And it still gets very nice geometry on the space we know very well, namely the sphere. Here is what it looks like to have like sort of balls in this geometry, the curves given by a specific distance. Here you see them compared to just taking the geodesics. Here you see, and you also see here is an ellipse, and you see that they don't actually follow exactly the terms of the ellipse either. So it's a whole special thing. Here is a direct test, just given some random points, where you do this minimization procedure. Here the arrows in 2D, it's very easy to give a symmetric matrix. You can just give the two eigenvalues and then the two directions. They are on orthonormal basis, and you just give their eigenvalues. So here, this is the largest eigenvalue given by the largest arrow, and then the smaller eigenvalue in this direction, and the base point is then the mean. And I scaled it a little bit so you can actually see the errors, because they should be a bit smaller. Here are some tests that you can find at this address for Stefan Sommer. You can check out this webpage. So this is again sphere, torus, and the hyperbolic space. And then let's, in the end, talk about this weird place with 40,000 people in Russia, in the Republic of Bergen, because I need to end the talk by answering the question I asked in the beginning of the talk. So this is the average between Fez and Shanghai, according to this. Thank you very much.